The focus of this video is understanding the basics of bivariate relationships. The term bivariate refers to two or bi variables or variate. So a bivariate relationship is the connection, relationship, or association between two variables. The focus of this unit will be on connecting two quantitative variables. Quantitative bivariate relationships can be understood using a special kind of graph called a scatterplot. It's also sometimes called a scatter dot graph or a scattergram. These graphs are used to represent the connection or relationship between two quantitative variables. One variable is designated as x and goes along the x-axis, and the other is designated as y and goes along the y-axis. Data are collected about x and y from multiple cases, and then each case is plotted based on its x and y location. For example, this dot has a score of 11 on x and 2 on y. Its coordinate is known as 11, 2. A coordinate is simply a location written as parentheses x, y, end parentheses. This dot has a location of 8, 3. And this dot has a location of 1, 8. While the dot just to the right of it has a location of 2, 8. So the coordinate helps us locate any of the dots on the xy graph. The first number in the coordinate gives the location of x, and the second number in the coordinate gives the location on y. Once all the dots or data have been plotted on the graph, we then look for any kind of trend or pattern in the dots. Let's look at this first graph. I see a fairly clear pattern here where the data are moving down from the top corner towards the right bottom corner, from left top to right bottom. So what I'm seeing is a general line, even though it's not a perfectly straight line, that is sloping downward. A linear graph or line graph is described as having a negative slope when we see that the line is generally angling down as we move from left to right, like in the first graph. Now take a look at this second graph in the middle. I'm not seeing any clear line here. The dots are scattered all over the place. So in this one, we don't seem to have a linear or line relationship among the dots. The scatter is very diffuse. So here we have no clear connection or pattern to our dots and no clear slope. Now we'll look at that third graph to the right. I'm seeing a pretty clear pattern along these dots that goes up as I move from left to right. In this third graph, there appears to be a positive slope. We have a general line forming, and it is pointing up as we move from left to right. So overall, we're seeing negative slope on the left graph, no relationship or clear line and slope in the middle graph, and a clear positive slope in the third graph. Graphs like the first one on the left are said to have a negative relationship, where graphs like the one on the right are said to have a positive relationship. The direction of the slope is also the direction of the relationship, because the line is the indicator of whether or not there appears to be any trend or relationship among the dots. In contrast, graphs that are similar to the one in the middle are said to have no relationship because there's no clear trend or line and thus no clear slope. When we're looking for a relationship or association between two quantitative variables, as statisticians, we call this a correlation. So the terms relationship, association, and correlation are basically synonyms. When we use a specific formula to find the correlation between two quantitative variables, the symbol we use for it is lowercase italic r. Just how we use x bar to represent the mean and lowercase italic s for standard deviation, we use r for relationships or correlations. If we calculate r, we'll find it always ranges somewhere between -1 and +1. If we see a correlation of exactly 1.0, that means that there's a perfect positive correlation. That's the strongest the trend can be when it's positive. If in contrast, we get an R of -1, that is a perfect negative correlation. That's the strongest a negative correlation can be. Sometimes we get correlations as low as 0. A 0 indicates that there is no correlation, 0 as nothing. So when R equals 0, two quantitative variables are unrelated. When R equals +1, it means that when one increases, the other one increases in a perfectly predictable fashion. And when the correlation is -1, it means that when one variable increases, the other one decreases in a perfectly predictable fashion. Few things are found to be perfectly positively correlated or perfectly negatively correlated in statistics. Instead, most things are found to be imperfectly positively correlated. For example, we might get R equals 0.85. This is a very strong positive relationship, but it's not perfect. Another example would be R equals 0.70. This is considered a strong positive correlation. The closer we get to 1.0, the stronger the positive correlation is. The same can be true for negative correlations. If we get an R equal to -0.85, this is a very strong negative correlation. If we get R equals -0.70, this is a strong negative correlation. Correlations that are close to but not exactly 0 are considered weak. So if I had a correlation equal to 0.10, that's pretty close to 0. That one's considered a very weak correlation. Similarly, if I get R equals -0.10, this is another very weak correlation. So when we're looking at an R value, we can tell two things: the strength of the relationship between the two variables and the direction of the relationship between two variables. When statisticians are interested in assessing the relationship between two quantitative variables, they start by coming up with a hypothesis. Hypotheses are statements of what a researcher or statistician expects to find. This is what the researcher or statistician believes to be true and is the basis from which they are collecting their data. Data are used to test this expectation. Desirable hypotheses are often directional. When we say that a correlational hypothesis is directional, it means that we've given some indication within the hypothesis as to whether we believe that the relationship will be positive or negative. Let's take a look at a few examples here. First, let's identify the variables in the statement, then we'll look for whether it's directional. The first statement says, those who study more tend to have higher grades. Think for a minute about what the two variables are here. The first variable is studying or time spent studying, and the second variable is grades. Now let's look for whether there's any indication of direction in this statement. Well, it says that those who study more tend to have higher grades. So I've got more with higher. That's increase with increase. Whenever we see increase with increase or decrease with decrease, it indicates that we're looking for a positive correlation. Think about what that graph looked like when we had a positive correlation. When we've got high scores on X, they're connected to high scores on Y. But when we had low scores on X, they were connected with low scores on Y. So when we see high scores with high scores or low scores with low scores, we're talking about the same line, one that's pointing up as we move from left to right. So increase with increase or decrease with decrease are both indicators of a positive correlation. Think about that for a moment. If I said the more you exercise, the happier you are, that has increase with increase. That's the same as saying the less you exercise, the less happier you are, decrease with decrease. Let's look at the second example. The more sugar you add, the sweeter the lemonade tastes. Think about what the two variables are in this second statement. One of them is sugar, and the other is sweetness, that is the sweetness of taste. Now let's look for indication of a direction. Well, we're seeing more sugar and sweeter, that ER at the end indicates more. So we have more sugar connected with more sweetness. So again, we have a positive direction. Next, the more you sleep, the less stress you experience. The variables are sleep and stress. Let's look for indication of direction. We've got more sleep with less stress. This is saying that when sleep increases, stress decreases. So in this one, we're positing a negative direction or a negative correlation. Moving along, let's look at the fourth example. Hours of exercise per week is negatively related to percentage of body fat. Let's start by identifying the variables. One of them is exercise, and the other one is body fat. Now in this one, we're looking for indication of direction. We don't have to look too far because it had the word negatively right in the sentence. So for this one, we have a hypothesis of a negative correlation or a negative direction for our graph. Next, income is positively related to years of college. First, we'll identify the variables. They are income and years of college. Now we look for indication of direction, and we see this one also was a little easier for us because the word positively was right there in the statement. So we know that the expectation is that there will be a positive correlation between income and years of college. Now let's look at the last one. Income is positively related to years of work. Well, here our two variables are income and years of work. And once more, we have the word positively in the statement. So the direction of the relationship expected is a positive one. So in 4 of these examples, we have a positive correlation hypothesized, and in 2 of these, we have a negative correlation hypothesized. Sometimes we can have a hypothesis where there is no direction. Let's take a look at an example. I could hypothesize that confidence relates to likability. Here, I'm saying there will be some relationship, but there's no indication of the direction. A non-directional hypothesis occurs when a researcher is a bit torn or doesn't have enough evidence to help them decide whether or not the relationship is expected to be positive or negative. I could think that confidence to a certain point is desirable, and so folks like someone who has confidence over someone who has no confidence. But I also might be concerned that if you're too confident, that people won't like you because they'll find you too boastful. So I'm not sure if there will be a positive or negative relationship. In this case, we would use a non-directional hypothesis. When we have a non-directional hypothesis, we're stating that there'll either be a positive or a negative correlation, but we're not sure which. The only thing we're pretty clear about is that there will be some relationship. That means that R will be something other than 0. Let's take a look at a real-world example of where we might see a positive relationship. In the stock market, we tend to expect positive relationships between stock prices within the same industry. That is, if one restaurant stock is increasing over time, we expect another restaurant stock to increase over time. The same goes for retail. I expect that if some clothing stores are increasing, in general, most or all retail stores or stocks are increasing. Now, when we say that we expect them to increase together, that means we also expect them to decrease together. Remember that both of these are indicators of a positive relationship. As the economy improves, we expect stock prices generally to increase. But when the economy slows, we expect similar kinds of stocks to decrease. For these reasons, we often expect to see positive correlations between stocks for similar companies. Let's take a look at the graph to the right, which shows a positive correlation. Notice here that though we have a straight line, it's not passing through all the dots together, but that's okay. When we see a straight line or a tight oval surrounding the dots, that's an indicator of a trend. Here, that narrow oval or line is pointing up, so visually we're seeing a positive correlation. We can look for the same kind of pattern in a negatively sloping graph. Take a look at our graph at the top. My dots are not all perfectly in a line, but they are in a fairly clear oval that's pointing down as we move from left to right. So we're seeing a negative trend here, though it's not perfect because the dots aren't all perfectly in a line together. We see something similar happening with this graph on the bottom, that though the dots are not in a perfectly straight line, we are seeing a trend going down from left to right. As noted earlier, sometimes we see or expect no relationship between two quantitative variables. For example, there is no correlation between the age at which we start teething and our intelligence. So if we were to gather data about the age at which someone first began teething and their adult intelligence, we tend to see a graph that looks kind of like the ones we're seeing here. We just see a scatter or cloud of dots. And if I try to draw my oval around them, I actually get more of a circle or square shape. So there's not a clear line forming anywhere. And even if I look at these dots, I might be tempted to say that I see a line going here, but I could also see a line going here, or even here. There's no clarity in the direction the dots are moving together, so here we have no correlation. So essentially, when we see a pattern that is circular, square, or even X-shaped, we find that there's no correlation because we're not seeing one clear direction to the pattern of the dots. One thing we must keep in mind is that you cannot have a correlation if one of your measured items is a constant. Both of the things you measure must be variables. Remember that a constant is something that has the same value for all persons. So for instance, I couldn't do a correlation between height and weight if everyone in my sample was exactly 5 foot 4 inches, because height would then be a constant. Take a look at our graph over to the side here. We have a graph with x as a constant 5. Everybody has an x value of 5, so even though things are varying along the y-axis, there's nothing clear in the pattern. Now we may be tempted to say that this looks like a strong positive slope because we see this trend generally pointing up, but it's not pointing up from left to right. Instead, it's pointing directly up. In order for us to have a graph that has a positive correlation, we need to see at least some slope in the line pointing up. It can be very dramatically pointing up, as long as it's not exactly vertical. If y was a constant, we'd see a perfectly straight line of dots moving horizontally. When x is a constant, we see a perfectly straight line of dots moving vertically. In each of these cases, no correlation can be computed because you must have two variables. In these, if you were to take these data and put them in the correlation formula, you're going to get an error. Your calculator or your software will say cannot compute because you do not have the right kind of data. As noted, when r equals positive 1.00, it indicates a perfect relationship. When there's a perfect relationship, we can draw a straight line that connects all of the dots because they're all perfectly aligned. When we have a perfectly negative correlation, r equals negative 1.00, and we can connect the dots moving down from left to right with a perfectly straight line. So in these cases, where we have r equals 1.00 or r equals negative 1.00, the relationships are referred to as perfect. But these kinds of perfect relationships are very rare in the behavioral sciences. So in areas like psychology, we're usually rather suspicious if we see a perfect correlation because these are so rare when it comes to human behavior. In fact, oftentimes when we talk about these kinds of relationships in class, like the perfect correlation of 1 or the perfect correlation of negative 1, it's in order to help us understand R, even though we don't necessarily see R values that look like this when we conduct research and collect real data. Though of course having a perfect relationship is theoretically possible, it's rarely observed in actual research. Let's take a closer look at one of the scatter plots that I had earlier. You might have noticed that one of our dots seemed to be hanging out far away from the pattern or line. It was rather far from the rest of the dots. When we have a dot that's far away, it's known as a bivariate outlier. It's called a bivariate outlier because the connection of its x to its y, bivariate, two variables, is distinct from what we're seeing among the other dots. Dots, however, that are similar to the rest of the trend, like I'll place this dot here, and a dot here, and a dot here, are not considered outliers because they follow the trend. I could place another one even further out here, but notice that it's on the same trajectory as the other dots. They're all moving up from left to right. So any dot that is on that line or close to that line, like here or here, is not considered a bivariate outlier. But when we have a dot that's all alone, far away from the line, vertically, very far from the line, it's known as an outlier. Bivariate outliers weaken the clarity of the correlation and thus they weaken the R value. Remember that R has a strength and direction. This dot out here, the outlier, is decreasing the strength of the relationship. If that dot were not included, the line would be clearer and R would increase. That means it would be closer to +1. That also means that each additional outlier weakens the correlation. I'm going to add another outlier near that red one, right here. This guy is weakening the correlation. I'll add another one down in the right corner. Another bivariate outlier is over here. Notice that as I add more and more of these guys, they no longer become rare or extreme, and the relationship or the line is becoming less and less clear. But if I get rid of those, the relationship becomes clear again, despite the fact that we still do see that one original outlier. Now, two things need to be true in order for a score to be considered an outlier. It needs to be extreme, that means far from the line, far away from the rest of the pattern, and it needs to be rare. If I add lots and lots of dots that are in outlier territory, they hit a threshold where they're no longer outliers because there isn't a clear pattern anymore. Notice here that as I've added many more dots, the upward pattern is no longer clear. That black line is not approximating the pattern of the dots anymore, at least not closely. It's very loose. So none of these guys are outliers in this situation because there is no clear pattern or line. However, if I get rid of all those guys, I could have perhaps 1 to 2 outliers. I've got one red one and one purple one up towards the left. And those are considered outliers because it's really clear here that there's a lot of dead space between them and the pattern where the rest of the dots reside around the clear upward trend line. When we're first learning about these graphs, it's hard to tell which of two graphs is the strongest. The thing that matters for determining strength is how close the dots are to a perfectly straight line. Presume that we have the same numbers along the x and y axis here. Compare those red dots and how close they are to their trend line. The trend line is that black line. The graph that has dots that are in general closer to the line is the one that is the strongest. So if we look carefully here, we see that the dots in the second graph are all really close to their line. There's not a lot of gap between them. When I try to color in those vertical gaps, I'm drawing very little on that right graph. But on the left graph, even though the gaps are small, I can still fill them in and they're more noticeable than in the second graph. So when we're comparing these two graphs, the stronger one is the one on the right, and the weaker one is the one on the left. Though both of these are fairly clear negative correlations. With that in mind, take a look at these 4 graphs and try to consider which one you think has the strongest correlation and which one looks like it has the weakest correlation. To do so, you're going to have to visualize what the line would look like that's passing through the approximate location of the dots. The strongest one, if x and y represent the same numbers along their axes, is going to be the one in the bottom left corner, because I can draw a line that bisects or crosses through nearly all of the dots, and there's very little gap between those dots and the line. The one in the top right corner also looks pretty strong to me, though when I draw my trend line, I do still see gapping from the dots to the line that is greater than the gapping I'm seeing in the bottom left graph. Now let's look at the gapping in the other two graphs. No matter how I position my line, I'm seeing a lot of gapping between the dots and the line, and I'm having a hard time drawing a line that cuts through and near many to all of the dots. So though it is obvious in all four of these graphs that there's a negative correlation, the strongest one is in the bottom left, and the next strongest one is in the top right. And though neither of the other two graphs are actually weak, they are weaker in comparison to the first two graphs, because the gapping between their dots and a line cutting through the center of the general cloud of the dots is larger. Take a look at these two graphs and estimate the strength of the correlation. You should be noticing that the correlation would be approximately 0 here, because I can't really fit any line that's going to cut through my dots. If I try to circle them, I really struggle, and I end up getting this kind of large oval-y shape or square shape. I'm not getting that tight oval pointing up or down when I try to encircle the dots. So for these ones, I'm seeing approximately no correlation. I'll try to draw them again to see if I can get more, but still I'm seeing a big circular shape. What I like about correlation is that when there is no relationship, r equals 0, and 0 has the same shape as these graphs. So you're seeing a big round cloud shape rather than a narrow oval pointing down or pointing up on your graph. It's an indication of no correlation. With that in mind, rank these three graphs from strongest to weakest. Assume that the x and y axes have the same numbers. You should notice that the strongest graph is the one on the bottom. That's because in this graph the dots are the closest to the line. But a lot of people are fooled by this graph and think it's the weakest, because though there is a clear positive slope and the dots are close to the line, a lot of folks will say that the line isn't pointing upwards dramatically enough, that it's looking fairly flat. That's irrelevant to the strength of the relationship. The strength of the relationship is only about how close the dots are to that line. And if the line is angling at all up or down and isn't perfectly horizontal or perfectly vertical, then there is a correlation. Then let's look for which graph is going to be the weakest. It's this one in the corner. Though the slope looks dramatic because the angle of it is pointing upwards more than the bottom graph, the distance from the dots to the line is actually pretty large. I'm seeing some big gaps between those dots and the line. The gap between the dots and the line indicate that the correlation is weaker. And these gaps are so important in statistics that they have their own name. They're called residuals. The term residual is used to refer to a special kind of error in statistics. The residual in these graphs is the error if we use the line to try to find the dots, because the dots are not on the line. But look at our strongest graph. The residuals are really small. There's not a lot of gap between the dots and the line. So if I use the line to try to locate any of the dots, I'm going to be really accurate because all the dots are very close to the line. So in summary, the closer the dots are to the line, the stronger the correlation. This is the same as saying the smaller the residuals, the stronger the correlation. Conversely, this means the further the dots are from the line, the weaker the correlation, and thus the larger the residuals, the weaker the correlation. Remember that a correlation coefficient, or R, tells us two things: the strength and the direction of the relationship. Strength is the same regardless of direction. So a correlation of 0.5 is just as strong as a correlation of negative 0.5. Pause here and put these correlation coefficients, or R values, in order from strongest to weakest. The strongest correlation is 0.98. There's a little typo here. It should say positive 0.98, not point plus 98. Nevertheless, our next strongest is negative 0.92 because it's the next strongest in absolute value, followed by 0.81, negative 0.76, negative 0.55, 0.44, 0.38, 0.31, 0.23, negative 0.17, 0.03, and our weakest is a correlation of 0, so weak that it indicates that there is no relationship. Now it's your turn to try graphing it with some scratch paper. Keep in mind that the coordinates go together. The first coordinate is 3, 2. The second one is 4, 4. The third is 6, 7. The fourth is 7, 6. The fifth is 2, 3, and so on. Pause here and create your graph, then hit play. I'll zoom in on my graph so it's a little easier to see. Note that at 2 locations, here and here, I have 2 dots there, not just 1. And there appears to be a fairly clear positive trend in this graph. So X and Y in this case look to be positively correlated. If we were to graph the coordinates of this second example, you'll notice something odd here. The dots are all forming a perfectly straight line pointing up. Because it is perfectly vertical, this indicates that I have a constant. The constant here is the 5 for X. So X is a constant. It does not vary. So for this reason, we cannot find a correlation here, and we can't talk about strength or direction. For extra practice on your own, you can try graphing these coordinates and assessing whether you believe there's a positive or negative correlation. And you can even take it a step further by trying to guess whether it's strong or weak. And you can then graph or plot these data to try to determine whether the X and Y variables here are related, and if so, the direction and relative strength of the correlation. Let's try another practice. Take a look at each of the scenarios below. Pause and decide whether you think each would have a positive correlation or a negative correlation. Then hit play for some guesses. Here are my guesses. I expect that height and weight will be positively correlated, such that the taller you are, the more you weigh. That the number of years of education and annual income in adulthood are positively related, such that the more time you spend getting educated, the higher your income. I expect that hours worked per week and classroom grades would be negatively correlated, so that those who are working more are getting lower grades on average, because I'm viewing this as a competing demand and there's only a finite amount of time students can spend on coursework and work each week. For average number of minutes spent talking to infants and toddlers per day and number of words those children use, I expect a positive correlation, that the more exposed children are to language, the larger the vocabulary will be that they develop. Size of a house in square footage and cost of the house, I also expect to be positively related. The larger the house, the higher the price. The smaller the house, the lower the price. I expect a negative correlation between good cholesterol, HDL, and severity of cardiovascular disease, but I expect a positive relationship between bad cholesterol, LDL, and severity of cardiovascular disease. I expect a negative correlation between sense of smell and degree of dementia because as the brain atrophies, I expect more loss. And finally, I expect the amount of fuel used and miles driven, since filling up will be positively related. That is, the more miles, the more fuel I've used. And that also means that the amount of fuel left will be negatively correlated to the miles driven. The more miles I drive, the less fuel I have left. Let's pause to summarize the key things we've learned. First, bivariate correlations are used to refer to the association or relationship between two quantitative variables. This means no constants can be used when we're doing a correlation. The symbol for the correlation coefficient is italic lowercase r. If we use the correlation formula, which we learn about in our college-level statistics class, the outcome of the formula is called a correlation coefficient. A correlation coefficient can range from -1 to +1, but it can't go outside of these boundaries. That means you'll never have r equals 2 or r equals -1.01. It isn't possible. R is used to summarize both the strength and the direction of a correlation. A negative correlation means that we have a downward slope, and a positive correlation means we have an upward slope. The closer our correlation is to 0, the weaker it is, with 0 being no correlation, and the closer our correlation is to 1 or -1, the stronger our correlation. We also saw that a correlation can be seen visually by making a scatter plot, where each dot represents the location or coordinate of an individual case. All the dots together represent the data set. A line can be made which is the best fitting line for the dots. The line is known as the line of best fit correlation line, or sometimes it's called a regression line. The fit line minimizes residuals. Residuals are the gaps between the dots to the line if looked at vertically. A bivariate outlier is a rare and extreme score. It's when we have a coordinate or a dot that is far from the fit line or trend line. That means it's far from the pattern we see in the other dots. Outliers have large residuals. If an outlier is removed, the correlation will be clearer and thus stronger. If an outlier is added, the correlation will become less clear and thus weaker. The smaller the residuals, the stronger the correlation, and the greater the residuals, the weaker the correlation.